Hello everyone, this is the libhal bi-weekly meeting. Today is January 20th, 2025, and here's what our agenda is. All right, so the first three items, I'm actually just going to verbally talk through what these are, and then we're going to go into more detail about some upgrades and changes to async context. All right, so um, Aaron has been working on his game engine, Engine 3D, and he's been using the llvm-toolchain, and he's been able to like produce a whole bunch of different things. So one of the things that I wasn't certain about was how far does the Windows support go? Because sometimes you'll be able to build a Hello World program and that works just fine, and you build some other things and that works just fine. But you keep pushing the boundary, and eventually you reach a point where like, oh, things aren't working. But at least right now we know that it works relatively well and he hasn't had any issues. There are limitations to Windows, just like how there's certain limitations with just different tool chains on different operating systems. For example, ASAN, address sanitizer, does not work on Windows. So if you're using that for debugging or for your unit tests to see if there's any seg faults or memory issues, that's not a tool that you have accessible on Windows, which is unfortunate. Um, and yeah, that's pretty cool. Next up, we have vendoring our fork of MP units. So I've got MP units integrated into libhal v5. I'll talk about that in a sec. But in order to make that happen, I needed to add some extra things, specifically a flag for disabling run type information. The purpose of this is that most of libhal and all of its uh, libraries are going to be built with RTTI disabled. It'd be really nice if I could just keep it enabled and then strip it out at link time, because then we could make everything just use RTTI, have it enabled, and then have it stripped out at link time, which feels like something that should exist. But I think the reason why that doesn't exist is because having RTTI disabled also prevents you from using um, I'm forgetting the name, not dynamic cast, but that's one of them that's also gets disabled. But there's also another thing that where you can get type info or type ID or something like that. Anyway, um, we'll be vendoring and like keeping up to date our own version of MP units so that we can add in little things that we need for compatibility with libhal. And the next up, for the updates, the only really big update, which took a bit of time because I ended up working on MP units, then async context, and some parts in strong pointer. But now that most of those are in a better spot, I have now integrated those into libhal v5. I now need to actually fully integrate them into everything. Um, so I'm still bringing over interfaces over from v4 into v5. And I need to change all of their return types, most of them to return back a future. Um, if they use some sort of unit, they're going to be using MP units. And then strong pointer will be mostly just used for callbacks. And like at least for the interface side of things. For the actual code, it'll be there too, and they can use it for anything. Um, and yeah, that's pretty much that. I'm hoping that now that I have a lot of this other stuff put together, bringing everything else over to V5 should be relatively quick, and then, or at least straightforward. I won't say quick, but straightforward. And then getting libhal util V6 up and available and using async context. Hopefully that won't take too much time either. And the real fun part will be migrating a lot of the code from libhal arm MCU over as well. The cool thing about that I kind of realized is that since um, libhal async the futures can be assigned to anything. Like you can just basically write your function synchronously and then return back your value. We should be able to port everything over just by changing the return value and then adding the first parameter. Um, and then all the implementations can, for the most part, stay exactly the same. They'd be blocking still, but they would stay the same. So that's kind of neat. And with that, now we have the async context updates. So first, I'm actually just going to do a little walk through the README. I spent some time kind of putting it together with the help of my like local large language model, Quinn v3 coder 30 billion parameters. It's not the best, but it I I'll work with it anyway. Um, Async context, a lightweight C++23 coroutine library for embedded systems and resource-constrained environments. Although this is mostly what the large language model came up with, I feel as if this system can be more generic than just being for embedded systems. It was built for these environments, but you can pretty much use it for anything else. Um, Side note, a little side tangent here. I spoke with someone about their coroutine implementation, and I fundamentally I don't fundamentally understand why they model a lot of their stuff with the idea that they have access to which thread or executor or thing to run things on. I feel like that's like a thing that you figure out at the top level versus figuring that out at the low level, like having a utility figure that out for you. That's just me though, but we'll just continue on. So it's built with a stack-based allocation to avoid heap usage and designed to fit within a single cache line for optimal performance. A little example of how the code would look, you use normal includes for whatever is here, unless you have import std, which if you do, use it. Then you have import async context. And we have a couple of APIs here. I'm just going to skip all the way down to main. Here we have, and I'm missing something in here. I need to update this. The word async should be in the front here, so that's a little mistaken. And there shouldn't be a scheduler either. So actually, this is actually kind of outdated. I thought I kind of went through and changed something else in this README, but I see that I need to change this as well. The scheduler is not necessary. This is not necessary. This should be all that you need, and you need a little async on front. We have this thing called sensor pipeline. You pass one context into the first one, pass a different context into the other one, and then you can basically round robin the loop through them. This is basically just taking an array of pointers to each one, check and see if they're done. If they're not done, there's a little variable called all done, which is set to true. You set it to false to say something's happened. Check the state, resume it. If it's blocked by time, just synchronously block by time, unblock it. Keep looping. Once you're done, check to see if they've all been done. If they have been, you can continue on. And the output would look interweaved. You can look at the, if you go to this repo, you'll be able to kind of look through it and see how things go. But yeah, that's kind of the idea, is you should be able to, this is kind of complicated in a way. There's a lot of stuff that's happening here. You're loading up stuff, and then you're round robining through it. But if you had a sufficient scheduler, like an event loop, it will be kind of straightforward. Actually, be very straightforward. All of this would be just a single function call for you. This talks about some of the features, stack-based allocation. So there's no heap allocation for any of the frames. Cache line optimized. The context, I tried my best to fit it within a cache line, and I was able to achieve that recently. You can check the state of the coroutine between being blocked by time, I/O, synchronization, or something external. We have a hook that allows you to, and I'll go into this a little bit later, to schedule things and a couple other stuff. One other picture that I really liked that I kind of put together is how the allocation works. So the idea is that this is your stack, and we're going to go downwards, but it's 0 to n. I just like going downwards just in general, so maybe that's a little confusing. But from here, we put our stack pointer into the stack, and then we allocate the coroutine frame afterwards. This is a bit of a really cool optimization that I realized. Rather than trying to keep the stack frame size, we know that when we delete this coroutine off of the stack, the address of it's going to be right here, meaning that we can go backwards one word, find the stack pointer, and then just move the stack pointer's value back to where it was originally, which would be like this line right before it. There's no change in the amount of memory that's used. This thing would have to either contain the stack frame, which would be like this, the difference between here and here. But rather than doing that, we have a much faster way of doing this, and actually saved like a 2 nanoseconds on my runtime. So cool stuff. And this kind of goes in and explains what's actually happening when you do allocation and then when you do deallocation. And yeah, it's fast, deterministic. It works as a dream. Yeah, so you can go through the examples to kind of see how things are put together. I show off, just doing normal basic stuff, waiting for 100 milliseconds, um, waiting for some I/O, what that would look like. What you would normally do is perform some DMA or set up some interrupts, and either at some state in the interrupt, if it's like a state machine of some sort, you'd have like oh, everything's finished, call and block, and disable the interrupt. Or you have DMA set up that'll go and do something for you, and this is your API to unblock the context when it's finished. Then you'll while loop, and every time you notice that the DMA is not complete, you will continue to block on I/O. You need this loop. Technically, you could work without it if your scheduler is sufficiently smart, but you can't guarantee that. So we want to make sure that code checks in with hardware to confirm that it is done. And if it's not, then it actually jumps into this. Also, this is useful because if it's already finished somehow by the time you get to this point for whatever reason, you don't even have to you don't have to wait at all. You can just completely return and then continue on with where you're going. Calling functions, basic stuff, implementing your own custom implementation. We'll go into this in a bit, so I'm actually not going to go into this too much here. And I'll actually come back to this in a little bit. So let's get back into this. All right, so async context. No more scheduler. Before we had a scheduler object and a context object, and the context object would always accept a scheduler, and that scheduler would come in through a strong pointer. I was mostly okay with this, but I started coming to doubt about. I started thinking about the fact that the scheduler, because of the whole connection we have here, if I have a strong pointer to a scheduler, the lifetime of these two things are bound to each other. That's obvious. That's kind of the whole point of using smart pointers. But then I thought to myself, it's almost as if I could eliminate the strong pointer if the lifetime was literally equal to the context, like it was the same thing. And this made me start thinking about whether or not context should have a pointer to its scheduler, or if it should just simply have a hook that allows you to access scheduling like information. And eventually, after thinking about it a bit, even though this is a bit of a change in the mindset here, I've decided to go with taking away the scheduler, the strong pointer to a scheduler, the smart pointer to a scheduler. Now we're going to have a virtual API. Context will now be an abstract class with a function called doSchedule. And what this does is, originally we needed 2 words for the smart pointer, one to its control block, one to the actual type. So this context would have been, it already starts at 8 bytes, or like 8 words. It starts 1, 2, 3, 4, 5, 6, 7, 8. It would have been another 2, so it would have been 10 words in total. So that would have been more than a cache line. I originally actually had a variant between the proxy information and the scheduler, which gives you back 1 word. Not really helpful. So anyway, I was able to save memory by moving over to this option. This now means that we do have a vtable. The first word becomes the vtable, pointer to the vtable. And there is some added ROM cost. You have to pay for 1 word for the offset to top in your vtable. You need another word for the pointer to the RTTI information, which is supposed to be normally a null pointer, unless you throw this thing, which would be silly. Destructor, deleting destructor, these are the things that make up the vtable always. And then after that are your APIs. So in this case, we have doSchedule. So we end up paying for 5 words per vtable for every unique implementation of your context, which I suspect for most applications, you will have 1, maybe 2. I could definitely see 2. 3 is weird if you have 3 different implementations of a context, unless, actually, let me pull that back. Technically, proxy is another context variant, so that would actually be likely. I guess 4 would be weird, but maybe we'll find out reasons in the future for people to have like 2 separate types of scheduling schemes for their contexts. Anyway, this also here kind of just shows you what makes up the context. It has a pointer to the active coroutine. That's what's supposed to be here, active coroutine. It has the address and length of your stack. It has a stack pointer as well. It has a block state, and then it has a bit of proxy information. If your context is a original context with its own stack, the one that actually owns the stack, then these both are null pointer. They don't point to anything. If these are proxies, then this will point to the original, and then this will point to the proxy's parent. And if the parent of the proxy is the original, then they both point to the original. The total cost here is 8 plus, like for a single context, and then for a single vtable. The total cost here is about 13 bytes, or sorry, 13 words. Multiply that by 4 or 8, depending on the bit system you have, or the number of bits of your system, and you get how many bytes that will take up. Yeah, but yeah, no, making this choice here resulted in a lot of memory being saved. I kind of already said this, but removing strong pointer removed 2 words, but it's brought this down to 1 word. This also removes the direct dependency on strong pointer, which also removes the dependency on polymorphic allocators, which also removes the dependency on needing another object that needs to be created through a smart pointer. Now, technically, you can make a strong pointer with a static object, so you won't need to always have a polymorphic allocator. But even then, even though I have no problem with these dependencies, I don't think it makes sense to make these dependencies of async context if we can get away with not having them. This simplifies the interface down, and one of the inspirations for this was if you're not really going to use a scheduler for anything, why bother with a scheduler? If you have control directly of the doSchedule function and you're making all your code synchronous, you just need the context to run your async code on top of, because that's just how we do things. You can check the block by state, check to see if it's by time, pull out the time that you have to wait for, and then just sleep for that duration of time. And I think okay, so yeah, that's pretty much what you can do there. Another thing that's also changed, before I spoke about being able to use this function called sync wait. After spending some time thinking over sync wait, I realized that it's actually a dangerous API to have, and I've actually removed it. It's been removed from future and context, and the main reason why is that I had another option here, but basically I decided to keep the semantic that block by time requires some external information. Basically, your application needs to tell us what to do, or to tell the system what to do when you block by time. If you have access to a threading library, you might want to use thread sleep. This thread sleep for. For RTOS, you might use xtask delay, or you can do something more clever. But the alternative to having the scheduler manage this is to have each one of the functions have a while loop for its delay, or we have some sort of special delay function that internally loops and checks the time. This would require maybe adding another virtual API to context called like now, so you can get the uptime or something like that, or uptime. I didn't like this idea, and then I fed that idea into like 2 separate large language models, Quinn and then also Claude Sonnet 4.5, and they both didn't like that idea either. They thought it was overly complex and ends up adding a burden to all of the other functions deeper in the coroutine stack for very little benefit, when we could just simply keep that there. So sync wait had to go. And yeah, there was no platform independent way to say sleep for. I could make context into some sort of like template thing, but now we're getting into things are getting really complicated once you start going down that route. So sync wait requires coordination with the scheduler, which isn't really possible when you're in a tight loop that sync wait was in. And yeah, so I removed it from those places and put it in its own implementation. That implementation is basic context. So it is a fully implemented context that supports sync wait. It also comes with a stack. You supply its stack through its template argument. You can pass it into, this is like a lambda that is a coroutine. It takes an async context, returns back a future, and does like a co-return 5. I'm immediately invoking it with the context, so it's a little funky here, but this is mostly just slideware because it just didn't have too many lines below here. But yeah, we get a future, and then you can use the context. You can sync wait and say, whenever we sleep, just call sleep 4. If you've used anything like FreeRTOS or some sort of hardware timer, you could replace this with whatever makes sense for your use case. I think our favorite use case is going to be timer.schedule, where you say, here's the amount of time I want to wait, and then you call wait for interrupt to basically wait for an interrupt to occur. Use a low power timer with this, and you can really get the amount of power consumption of your system down by a great amount. Oh yeah, and another thing about this is that the stack memory for this is actually embedded inside of the memory of this object. This simply just means that the lifetime of the stack is bound to this thing, and it's not dynamically allocated or anything like that. It's just within itself. And one requirement of all contexts going forward is that their constructor, and I'll show you this in a little bit, must initialize the stack, and its destructor must cancel. Later on, after I get to the end of this whole presentation, when I go back to the README, I'll explain why that has to be. All right, so another thing that I want to go into, because we have actually a new state for futures. A new feature is cancellation. I think I might have brought this up before, but I realized if I had talked about it that it wasn't complete. It wasn't a complete idea. What I was thinking about before was technically you can call a future or call an async function, get a future, and keep resuming it, and then at some point just destroy it. If you just call destroy on it, it'll wipe out the entire coroutine chain, and that should be good cancellation. But I spent some time thinking about what exactly cancellation means and how it would affect code, and a couple realizations before I get into the diagram here. Cancellation safety, meaning when you cancel something, everything is put into a good state, is identical to error handling safety. And I don't mean exception safety, I mean just error handling safety. To make that kind of clear, if you have a function that opens a file and you return back an error, but there's no RAII to make sure that the function that was created gets closed, or you don't have some other type of scope guard or something like that to make sure that the thing gets closed, then it won't get closed, and you have a problem. And that can happen no matter if you threw an exception or if you returned back an error through did expected. So when I made that realization that cancel safety is the exact same thing as error safety, we expect people to have error safe code, to write code in such that if an error occurs, things unwind itself properly. We get cancellation safety for free, which is nice. So here's what happens. Let's say that you pass a context into some coroutine. It can either return back to you done, meaning that it's synchronously finished and here's your answer, here's your thing, or it starts up an async operation. It hasn't started it yet, but it basically constructs it and says, hey, I'm busy. What happens here is that you can basically loop around the busy state over and over and over again until, and actually this arrow should be in the other direction, but yeah. You loop here until eventually either busy becomes the done state, or if an exception was thrown somewhere during the line, it then propagates up to the future itself, and then it gets set to a exception pointer state. And then finally, we have a canceled state. This one's kind of rare. This only can happen from like a top level point of view, but not super important. Basically, we have the fact that you can go from busy to canceled or to an error state or to done. And these are the 4 states that a future can be in. Another big update with async context is that cancellation is fully supported. That includes calling destructors on things on the coroutine stack. That all just works. I'm actually just really happy with how the coroutine code is starting to come together. But I want to show you some of the safety that comes with cancellation. So we have async basic context with 1024 words for its stack. We have some scope. We have a future, set up some asynchronous operation with the context, resume it a certain portion. If you created the future and then dropped it, fine. That's usually perfectly fine. I believe we will still call destroy in order to destroy any variables that were copied in that have lifetimes, but you're usually allowed to just destroy the object. If you resume it, now you've made some progress, so you now have to destroy any other coroutines that might have been allocated at that time. When the scope ends, the future will cancel itself. That will free up all of the memory that's on the basic context, making it available to be used for anything else. It'll also ensure that there aren't any dangling resources out on the context. That could also be overwritten, and it'll be a whole bunch of UB if that occurred. Also, outside of destroying it through lifetimes, you can also do .cancel, and that'll also cancel the entire operation up to this future. You can't call cancel on you co-await a future, you've lost the ability to actually call cancel on that thing. Usually, unless you do pass it in and call cancel directly, but that'd be silly. That'd be a waste of cycles and time. So this works. Also, another cool thing is that if you call context.cancel on a future, on the context associated with the future, it will also cancel everything, but it will also reach in and update this future to be in a canceled state. This is important because if we did not do this, the future, if it's in the busy state, would still be in the busy state, but that coroutine handle is pointing to a promise, pointing to its coroutine frame that does not exist. And if you resume it, that's undefined behavior. And I didn't like the idea of zombie futures hanging around. I also need to figure out a way to save these futures in a type erased fashion so that we don't need to kind of keep them exactly around. I'm wondering what we do for tasks, because in a way they don't need to really have a future associated with them, but that's for another time. And then if you somehow had a future outlive the lifetime of a context, and the context is destroyed, its destructor will also cancel. And that'll ensure that that future state is turned to canceled. And then any access of that particular future, resume on it, will throw an exception. And I want to go over the cancellation process so you have an idea of how it works, because there's kind of two ways to go about doing it. Consider a context that has 4 promises on it. So we have promise 1, 2, 3, 4, and the associated futures for each one of those. This future here is outside of the context. It's either on a stack, it's on a thread stack, it's global, it's dynamically allocated. It could be something which is not a part of the coroutine frame. The first thing we do is when we call cancellation, it begins at the active coroutine, which is the one at the bottom. Using the active coroutine handle, it calls cancel. The cancel API will set the associated future, this future here, to the canceled state. It'll pop itself off the coroutine active state, basically taking the return address of this promise and basically setting the active coroutine to it, which is basically saying go back to the previous promise. And then it destroys itself. Now, we're going to go from bottom up this entire process. I just want to note one thing is that technically we could have gone top down. It's actually faster to just go top down because it would be immediate, and although it would just iterate through from future 1 to promise 1 to future 2, promise 2, future 3, promise 3, all the way down to hitting the last promise, and then recursively, do all of the destructions up until the point where it finishes. It works perfectly fine. The problem is that the amount of stack memory you need for calling all of those deep and deeper and deeper destructors can be somewhat dangerous. So my approach is just to delete, destroy, 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 keep the destructor's depth as short as possible. So we keep popping things off, we continue to loop, and each time we do that, the active coroutine gets changed to the thing above it. And we just keep doing this until eventually the active coroutine becomes the no-op sentinel. We basically have a no-op coroutine. We use the no-op coroutine to kind of represent finishing. And now everything will be in a canceled state, and this will probably all be completely deallocated at this point. So that's pretty much that. I do want to show off one last bit, which is, let's see, I want to show off proxy, and then I also want to show off it's not super important. Yes, just a custom context implementation. So here we have my context. It implements or inherits async context. It has an array with a stack in it. I don't know why I put this in the public section. There's also something I should change. Unless you want to inspect the stack yourself and create some UB, not really a good reason to have this thing be public. There is a function that's provided by context called initialize stack memory. You pass your stack memory into it. If you're going to dynamically allocate the memory, you would do so, then pass it in here. And on the flip side, when you destruct, the first thing you would do is cancel everything and then deallocate your memory for your stack. This is a bit of an annoyance, and I don't think CRTP solves this for us, I don't think. The main thing is, I thought I could put cancel inside of context. I actually had it, I kept putting it back in thinking that, oh, it'll work, and I could figure out why it doesn't work, and I kept having a hard time figuring out why it wasn't working. And then I started looking at the actual error and what was written in it, and it said, stack use after free. And all that told me was that the myContext object gets destroyed first. Then context gets destroyed. That means that its array, its stack memory, is technically destroyed. ASAN was telling me that you're referring to a stack that, or some memory that does not exist anymore. So you can't cancel off that. It doesn't exist. So now what actually has to happen is you need to have this object cancel before this goes away at all, and then this can go away, and then the rest can be destroyed. And I think context destructor does nothing now. So that's how you would create your own context. I think this is relatively short, and then you can put in what you want to do when one of these states changes. This is probably one of those things that ends up being quite complicated, or can be quite complicated. You can make it simple, you can make it complicated for yourself. There's a lot of options here. And if you had a more sophisticated scheduler, you can have that be an input parameter, and then have like a smart pointer to that scheduler, and then pass any and all schedule information from this function call into that scheduler. And then that scheduler can do what it needs to do to figure out how to sleep for durations of time, call the right things, all of that. Yeah. I think I already mentioned this, just making sure, but yeah, exceptions work as you'd expect. They do propagate through the entire coroutine chain. I had an option to have it propagate directly out of the resume call. That would be awful. You couldn't write any code that way. It just didn't make any sense. So yeah, so exceptions propagate through. I don't remember if I spoke about this too much last time, but I want to just reiterate it again. I don't have a solution yet. If anyone has an idea of a solution to this, I'd be interested. But basically, operation stacking. If you have a context and you put one operation on it, and then put a second operation on it, a couple things have to basically, you're in a bad position. This is fine. This is problematic because now you have a memory leak. If this operation or any of your parameters had a lifetime associated with it, those variables are also memory leaked. So if you put like a standard string as a second parameter here, if I'm not mistaken, that would also be memory leaked. The reason why is that once you call this, you set the active coroutine equal to whatever promise comes from this. When you do this again, it overwrites the active coroutine, and it doesn't like have any sort of causal connection to the previous one. So after this finishes, we have no way to access the previous one. Therefore, we have a memory leak. And then the moment you destroy the context, you now are in UB land because you basically have objects that might still be in the ether that think they're still around, which could be very dangerous. I'm still thinking about ways to make this happen. If I can somehow just sneak the active coroutine of the context into the next operation, what we could do is finish this operation or cancel this operation, which then can also cancel this operation. So that ends up working just fine. Or we... Oh, is my screen broken? Oh, okay, hold up. Give me a sec. Can you guys see my screen? Testing 1, 2, 3. Can you guys see my screen? Hello. Testing. Testing. Can you guys hear me? I guess you guys cannot hear me.
Just speaking again.
Testing 1, 2, 3. Can you guys hear me?
I can't hear you.
Interesting.